Hi and welcome to this week's Introduction to Structured Programming. We are in week 7 and today we talk about memory. So we leave the pointers a bit behind, but we will use them. Yeah, we will use them very often today again. Yeah. So memory. What is memory? We will talk about that soon. Before that, we will talk about casts and some other small data types we might use. But the main topic for today is memory layout and general memory. Before that, as always, some organizational methods. We are in week 7, so today is also the handout of the weekly exercises number 7, and they also belong already to assignment 3. So the deadline for that is the 10th of December. So it's a month. And as always, just as a reminder, you get a 25% point deduction if you do not pass more than 50% of all of the assignment 3 related weekly exercises. Okay, I think that was it already. Let's move on to the recap. And as always, put out your phone. We have 3 questions for you regarding pointers and strings also in this case.
So yeah, last week we talked a lot about strings, also the week before. And now we have a code snippet where we first define a string using a character array. After that, we also define another variable of the type character pointer, and we want to store the value of the character array in our character pointer. We also want to modify the first value, so the value at position 0. And after that, we want to print the original variable, so the character array, but also the character pointer. And we want to see if this works, and if it works, what will change. Will both variables change? Will only one variable change? Let's see.
I would say it's an easier one to start. Let's wait for another few seconds for you to decide. Okay, so. Oh, okay.
Wow, interesting.
I thought it's easier. Okay, so now it's getting better.
As always.
So the correct one is my pet red, your pet red. Why is this the case? So we have a character array here with cat. We have a pointer, so we create here a pointer to the array. So it's basically just a pointer. So your pet here is basically a pointer to the first element of the array, of the my pet array. So my pet and your pet are pointing to the same string. They are pointing to this C here, which is the start of the string cat. And if I now change the 0th element of your pet, I will also change the 0 element of my pet. And that's why both cats become rats. So this is the correct one.
And since it is just a character array, we can modify it, we can change values, so that's totally fine, because we do not define cat as a character pointer, so as a string literal, but as a character array. That's why it works, and the cat becomes a rat.
Okay, let's continue to this one. It's a bit more complicated, I think. It includes, again, arrays, but also pointer arithmetic, which you also saw in the practicals before.
So I had to use a sheet of paper.
It's that hard? Okay.
At least for me. Yeah, I think we can wait another few seconds.
Yeah, that's harder. I have to admit, yeah. But if you know the first, so the value here, you can maybe infer the other value, because then the possible answers are much less.
Yeah. Still a lot of discussions going on.
Yeah, of course you can discuss with your colleagues and your neighbors what you think about that, but they might think.
Okay, maybe 10 more seconds and then.
Yeah. Okay, let's see what you voted for.
Great.
Okay,
Yep.
here we have great results. Great, yeah, it's 11 and 39. Why is this the case? So we have the array here with 10, 20, 30, 40, 50. And this line 6 here, so dereferencing array is just a pointer of the first element. So dereferencing array gives us the value 10. So value here has 10. We increment this 10. So the first number here in the printf is 11. I think that's the easier one. The second part, let's see, we have array here. Array is a pointer to the first element. We add 2 to the pointer of the first element. So we are pointing now to the third element. So we are pointing to this 30 here. And then okay, it's really complicated. We increment this pointer by 1. So this pointer is a pointer to 30. Increment the pointer, so we go to 40 because we are incrementing the address. And then we dereference this value 40 and reduce it by 1, which makes then 39 as output.
That's awesome. So many of you got it right. It's really great.
Okay, one last. I wrote there some statements about this code snippet, and you have to say which one of them are correct.
Maybe
So
again, 10 more seconds.
yeah, the results are very evenly distributed. It's interesting. Okay, let's see again what you voted for. The value of arrow at line 7 are 1, 10, and 33. Let's see. 1, we override the second element with 10 and 33. That's correct. Array plus 1 in line 6 adds 4 to the address of array. That's also correct because, so we're adding 4 bytes. Did I write bytes? No. Adds 4 to the address. So of course it should be 4 bytes. So this array plus 1 adds 4 bytes to the address of array. The function returns an invalid pointer. That's also correct because we have a local array here. Never return a local array from a function, so that's also not correct. Or that the statement is correct. Then printf of size of array written in line 7 would output the value 3. That's wrong because we have integers here with 3 elements. It's always the data type times the number of elements. So in this case, we have 3 elements with 4 bytes. It would output 12. And dereferencing array plus 1 can also be written as dereferencing array plus 1 without the parentheses. No, it's different. The value of array at position 1 is 2 at line 7. No, we have overwritten that here with the value of 10. Okay, any questions to this one or to the other quizzes before? If that is not the case, then we can start with casts.
Yeah, so we've already talked about converting values between different data types last week, and we talked about command line arguments. So we only had strings, so just character pointers. And of course, sometimes we want to have integer values, but also float values. So we don't always want to have string values when we pass something as a command line argument. What we did, we just used some functions which are provided in the C standard library. For example, we had a look at a to I, so ASCII to integer, which converts just ASCII string, just a concatenation of characters, to an integer value. And we can then just work with the integer value, which is stored in an integer variable. The same or we can do the same thing with the function a to f. It's just ASCII string to float. So again, we can convert something which is of data type string to something or a value which is of data type float. So that we can already do. That's totally cool. But what can we do, or what do we have to do if we, for example, want to convert an integer value to a float value, or the other way around, a float value to an integer value? And for this, we can use type casting, or it's also called type conversion. And this is basically the same thing as the functions do. It means that we convert a data type A to a data type B. So a value which was of data type A or is of data type A can be typecasted, so converted to the value of data type B. And C provides 2 different types of casts. The first one is the implicit cast or implicit casting, and there we don't see anything in the code, but the compiler converts, in this case, the integer variable, so the value 4, to a float variable, which is then stored in the new variable y. So there's nothing we can see. This happens implicitly. The compiler does it for us, and it works. So in the end, we have the value 4 as a float value in our variable. But we can also explicitly cast, so explicitly convert from data type A to data type B. And the syntax for that is, yeah, I would say quite easy. We just write in parentheses the data type that we want to convert it to. It's called the cast operator. We can also see it here. So we just write float before the variable name x, which is of data type int. And as a result, we will store the float value of 4 in this variable y. So in this case, both casts, the implicit cast, but also the explicit cast, lead to the same result. But there are some use cases, we will see some of them, where we need an explicit cast. I think we also had it in the very first lecture where we wanted to divide to integer values. And we didn't get the result that we at least expected.
Yeah.
And we can solve this issue if we convert, for example, one value to a float data type and then to the division. So that's one, I would say, a common use case for explicit casting. So cast operator is quite straightforward. We just write parentheses, and inside of these parentheses, we write the new data type, so the data type that the value should be converted to. Now, it becomes interesting. So let's assume we have an integer variable, which holds the value 257, and we want to convert this integer data type to a character data type. Are there any ideas what could happen here if we want to convert the value 257 to a character data type?
We already discussed that in the first lecture about variables and data types. Any idea what happens here? Yeah. Okay, so we get the ASCII value of 257. Another idea? Yeah. Yeah, probably we get a 1 because of the overflow, and that's actually correct, because a character can only store the values from 0 to 255. Then it starts with 0 again. So this is the first lesson here, I would say.
Yeah, that we always should take care when we explicitly cast, or in general when we cast from one data type to another data type, there's always a risk in certain situations that we can lose some specific values or have some unwanted behavior. Like in this case, we would expect to have the character value 257, which does not exist. Yeah. And that's why we get the result 1 here. Yes, there's a question. Oh. Sorry?
If signed make a difference?
Yeah, it's signed. Yeah.
It would make a difference. No, it goes 2 rounds maybe, yeah, but it wouldn't make a difference, yeah. Okay, next problem. We have defined pi. Not very well, yeah, no. But we've defined pi, and we do it even worse. Convert it to an integer. What happens here if we explicitly cast it to an integer? Yeah. It gets trimmed. Yeah, exactly. So the output is just free. A very, very rough definition of pi.
I think there are some fields where we calculate pi with 3. I don't know other fields. But yeah, so if we don't explicitly want to use 3 as the value for pi, we shouldn't do this.
So the lesson here is only cast if you're sure you do not lose information, of course.
So
does this one work? Yeah.
Now it's really tricky. So we have a character array which stores just a concatenation of single characters, and we want to convert this string, so this character array, to an integer.
I think we already had that a few slides before. No, there are functions for that. If we do it like this, we actually cast the address. So the address of the first character to an integer, which is some random big number. And the output is something like this.
Yeah.
Makes no sense. Yeah. That's why we use this atoy or strutol.
Exactly. So we have functions for that, for converting strings to integers or floats or long variables. All right, but now we are getting closer to pointers and dynamic memory. Of course, we can also cast pointers. Yes, pointers all have the same data size, same size of the data type, so it's always 8 bytes. Independently, if it's a float pointer, if it's an integer pointer, character pointer, it is always 8 bytes, but in some cases, and also for readability, it definitely makes sense to have the concrete data type. So for example, if you have a float array or just a float pointer, which stores the address of a value that contains a float value, it definitely makes sense to really explicitly write the exact data type. And we can also convert between different pointer data types. So we can convert between float pointer and integer pointer and so on. But there's also one special pointer. We didn't mention this pointer last week. It's called the void pointer. And this void pointer means that we can use any data type and convert it, for example, from a void pointer to the desired type of pointer that we have. For example, if we have a character array, we can just always use a void pointer and then convert it to a character pointer.
I have to admit, this is a very not very intuitive example, but we just want to show you that there are possibilities to convert floats to floats, getting the address of floats to convert it to a void pointer, do something with it. We will have, or we will see better examples today, the lecture, in memory management later on. Yeah, it
will make sense once we come to dynamic memory and to specific functions.
Yeah. But just as a takeaway, void pointer can be any pointer.
Yeah.
Okay.
And we also want to discuss an additional data type, which is quite important also when we talk about pointers and dynamic memory. And this data type is called size t. Essentially, size t is just a type for unsigned long. So assuming a 64-bit architecture, it's 8 bytes. And the great advantage of size t, of this data type, is that every value, or let's phrase it in another way, there can't be any negative values that are stored in a size t variable. And why do we even need a size t? It's commonly used in different functions. For example, you have already used the size of operator, but also, for example, strlen and many other functions that we will discuss today. Use size t because size t guarantees that the value cannot be negative. So a negative value for strlen would be weird, I would say.
Yeah.
And another advantage of size t is that it can store the maximum value of an object. So we'll see a definition of that soon. But with size t, it's guaranteed that it's not negative and that it can store the largest possible number of bytes an object can have. All right. So what would happen if we now just store the result of the size of operator in an integer variable? We would get this warning here. It would say the format specifier is not correct for this variable. And that's why we have to change the format specifier when we print a size t variable from %d to %lu, so just a long unsigned value. And yeah, we've just mentioned it. Why should we even use the size t data type? Because with this data type, it's guaranteed that we can store the maximum size of a possible object, so there cannot be any object that is larger than the maximum value of size t. And this is quite useful for arrays, but also for example, loops, because it would be really bad if we would assume a positive value and then wherever there's a negative value and we have an infinite loop. So that's why it always makes sense to use size t when we work, for example, with arrays and also with dynamic memory. And yeah, as mentioned before, we also have this special type of pointer, which is called a void pointer. We've already heard that void can mean actually nothing, so it can be anything, nothing, and yeah, arbitrary, German beliebiges. So we can also use the void pointer to store any kind of data type pointer in this pointer and later on convert it back to the desired pointer data type. So we have also a code snippet here where we pass a void pointer as an argument to a function print value, and then we can distinguish between the type which is also passed, and depending on the type, we then just use the typecast that we have learned before. We have an explicit typecast int pointer if the data type is int, a float pointer if it's a float, and a character pointer if it's a character. But the cool thing is that we can pass the void pointer and later on decide which type of pointer is it really. So if it's a float, an integer float or a character pointer. So that's really cool, and we will use that heavily from now on.
Yeah. So this void here means nothing. This void here means arbitrary, so can be any type of the others.
And yeah, one important thing that we almost forgot is that you cannot dereference the void pointer. So you have to cast the void pointer explicitly to, or in general, just cast it to another data type, can be explicitly or implicitly, but you cannot just dereference a void pointer. So if we would just print and dereference the void pointer, this wouldn't work.
Okay, so I think now we have everything we need to talk about today's lecture topic.
I hope so, yeah.
So we have all the pointers, the void pointer, the size t, all the knowledge from the past few weeks where we talked about pointers. Now when we talk about memory, we talk about the heap and dynamic memory. We will use all this information we have seen in the last few lectures for a very, very important and interesting topic. Before that, before we come to the heap explicitly, I want to talk about the memory layout in general. And when we talk about memory, we always talk about this one. I hope most of you know what this is. I hope you might have seen that before. When we talk about memory, we do not mean the storage, so the file system. That's not very interesting for us. When we talk about memory, we talk about the RAM. That's our main memory. That's the interesting one for us, because this is where we do our calculations. This is where our program works, runs, and so on. And you can imagine when we talk about memory, like there is a grid over this, one of these memory segments here. And okay, let's remove the memory. Let's say it looks something like this. So this is our RAM. We have addresses here. We have bytes inside. So this one has 2 bytes, and there are some zeros and ones inside. Here are also 2 bytes stored, some value, whatever. So this memory here can store 48 1-byte values. If you have an 8 gigabyte memory, which is nowadays not that much, it can approximately store 10 billion values. So, of course, it's a lot more, but we want to show it in a very, very small way here. Okay, so what is the memory layout of a RAM? We have 2 main segments inside. The first one belongs to the operating system. So everything of the addresses 0x7FFFF, so everything of 0x8 and above belongs to the operating system, so we cannot touch this as a user. Everything below that, so the half below, is called user space. This is where our programs are running, and this is the actual address space we can use. So yeah, let's forget about the operating system space here. You have operating systems later on in your studies, and then you will focus on this part. Here we are focused on the user space. And the user space uses some segments we might have discussed already, especially the stack. We already mentioned a few times the stack. Stack is just one part of the user space. The other one are the heap, the data segment, and the code segment. Let's see what this is. So the code segment is the segment in the memory where your program lies. So this is where your actual program is stored to be executed. Then you have the data segment. Here you have constants or global variables. Then we have the stack, which we have used a lot, or I would say 99%, where local variables are stored. And then there is the heap for the dynamic memory we will discuss now in a few slides. So again, if you have this function here, this main, and we have a local variable, and you print the address of this local variable, we see something like this. So an address of 0x7FFFF, very, very high on this user space. So local variables are always inside functions, are stored on the stack. Constants, for example, like this, if you define it with const, are stored in the data segment. Data segment is here between the heap and the code segment, and mostly have addresses around 0x55, whatever. Now it's getting difficult. Also, our code has some address. So when I create my function here, and I print the address of this function, I get an address, and this is here in the code segment. So our code also lies somewhere in the main memory to be executed. And we also discussed that a few times already. We have a char pointer here, and we have a char array here. We already discussed the differences, and I always said there is the char pointer is in another memory segment. So when I print it like this, you can see the char array here has an address of 0x7FFF, which corresponds to the stack. That's why we can modify it. The other one, the char pointer here, has an address of 0x55 whatever. This is an address of the data segment, and most parts of the data segment are not modifiable. There are constants there. Also global variables are there, and also the char pointers are stored there. So the data segment is a different part and yeah, char arrays are stored there.
That's why we can't modify them. So
Yeah,
char pointer cannot be modified. The char array can be modified because they are the stack if it's a character array, and in the data segment if it's a character pointer.
yeah. So we have seen now the stack, the data segment, the code segment. Now the interesting part is, of course, what is the heap? What is this here in between? I want to start here with a short motivation. We again heard it today in the lecture. Again, we heard it today in the recap. But if we have a local array in this create array function, and we return this one. So we have the array here in this create array function. We have the length, so this parameter here in this stack of the create array. We have the I value, I variable here. And as soon as this create array is finished, we cannot access this array anymore because the stack of the create array is already gone. So we cannot access it here. Wow. We get a warning, luckily, when we do something like this. So the compiler already tells us you're returning an address of a local variable. That's not a good idea. Most likely your program will crash. So that does not work. Now for the heap, we have a solution. The heap solves this problem. So the data that is stored on the heap is also called dynamic memory. Why dynamic? Yeah, because it has some differences to the stack. The stack is, as you can see here, like one variable over each other.
Kind of structured.
It's very, very structured, yeah. The heap, in German, I think Haufen, yeah, is just very random packages of data. So there is no real structure inside. It's just a heap of different memory locations, and there is no real structure inside. The cool thing is the data of the heap is not limited to the lifetime of functions, which means if a function ends, all the variables on the stack are removed, but all the variables on the heap are not removed. And this solves our problem from before, where we had an array inside a function. We just have to use the heap for that. There is one downside to all these advantages of the heap, that we as a programmer have to take care to remove this memory we have used. So when we want something from the heap, and it's not automatically removed by, so as it is with the stack, we have to remove it. That's the downside, but we'll come to that later on. Okay, the keyword for allocating memory is, I think, very intuitive, memory allocation or malloc. Let's try to use our problem here. Let's try to use malloc to solve our problem from before. We have again our create array function, but now we are calling malloc with 5, which gives us 5 bytes on the heap. We store it in a pointer. We return the pointer, and then we can also access it here. So the lifetime of this array we are created here is not bound to the create array function, so it can be accessed afterwards. So this code, if you access here the array, will work. Let's see how this works. So when we call malloc, we don't have the array stored on the stack anymore. We just have a pointer to the heap where my variables are stored then. So malloc returns me a pointer to the heap where my array is stored. That's a very, very cool thing, because now when I return here my pointer, so just one variable which stores the address where my actually array is stored, this one gets copied from my return. So my array pointer gets copied here into my jar pointer array, and they are both pointing to the same memory on the heap where I have my array here. And okay, my R pointer here is destructed because the create array function is destroyed, and all the local variables, and this R here, this pointer is a local variable, is also removed. But what I still have is a pointer to my heap array.
But as you mentioned, we will talk about it in a few seconds. If we would not store the returned variable, so array here,
Yeah.
what would happen?
If we do not catch this pointer, we will lose the information, because we have the information here, and if we do not copy it back to our main function to keep this connection to this array on the heap, then we would lose the information. So the array still here is allocated for me, but I cannot find it anymore because it's somewhere on the heap, and the heap has no structure, so I don't know where it is.
We just lost the pointer.
Yeah.
Yeah, that's not good.
That's basically the concept of dynamic memory. Of course, it gets a bit more complicated, but if you understood this one, it's a very, very good first step. Any questions to this?
Mm-hmm. So the question is if you lose the pointer multiple times, if I got it right. Yeah. So yeah, of course, every time you lose the pointer, it's definitely not good, because there is something in the heap that is actually allocated for you, but you cannot access it anymore. So if it just happens once, okay, yeah, that's bad. But of course, if this happens, let's say for a large array, multiple times, hundreds of times, thousands of times, yeah, you will run out of heap memory. At some point, you will not be able to allocate any memory on the heap anymore. Of course, you have to allocate a lot before that and lose a lot of pointers, or lose the pointer that points to a large array. But yeah, at some point, you run out of memory in the heap.
But we will come to that in a few slides. Yes. Very, very good question. The question is, character pointers are stored in the data segment. So the question is now, is this one stored in the data segment? And the answer is no, because I know that it might confuse you, because this here is another type of character pointer to the one we've created before. If we write it like character pointer string is equal to and then some string, then it's stored in the data segment. But if we call malloc, malloc always returns a pointer to the heap, and it gives you the address, and most likely you store the address on the heap. So this is a pointer to the heap where you can store characters. Stored on the stack, yeah. Sorry?
I think
So nothing is stored here in the data segment. This R here, when we go back, this R here is stored on the stack of the create array function. And this one is just an address, the address of the first element of the array on the heap.
So
on the stack.
The pointer is just a variable that is stored in the stack, in this case of the main function. So just a local variable just of data type pointer, which is stored on the stack in the main function. But this so if I got it.
Okay, so what you have here, you can replace this R by the value of it. The value of this R is an address, OX5, whatever. And what you do with this return here is you copy this value, OX5, whatever, into this R array variable here. So you basically copy this into that stack. You stay on the stack from this create array function into the main function. So here in the main function, the value of array is OX5, whatever. And as soon as this create array function here is destructed, you lose the information. You can see here there's nothing inside anymore. But you still have the address on the heap where I want to store my values.
So yeah, the variable
the R disappears. Yeah, the actual R disappears, but I keep the value by copying it into another variable. Yeah, the actual R disappears. That's what we said always. Variables on a stack only live as long as the function runs, and as soon as the function is over, all the local variables stored on the stack are gone. So everything what is defined inside this create array function as a local variable is gone as soon as this create array function is over. Why does this variable ARR have to be a pointer? Maybe we come to the next slide and there we can discuss that. So malloc takes one argument, which is a size t we've heard before, with the size of the number of bytes we want to allocate. And malloc returns a void pointer to a location on the heap. So in this case, void means arbitrary, so it could be basically everything we want to have, every type of pointer. It can be a char pointer, int pointer, or whatever. But very, very important, it returns a pointer to an address. Well, not a pointer, which is an address, and the address is the memory location of my array. So we always have to take a pointer back from malloc to see where is our memory.
Yeah, and that's why we have to use the data type character pointer, because malloc returns a void pointer, and as we've heard before, we can just cast it to a character pointer. We don't even have to explicitly cast it. We can just write malloc and assign the return value to the character pointer.
Yeah. Of course, you can also use the malloc in the main. We just want to show you like the solution that you could use it like that. But we will see many other programs using malloc in the next few slides, also next week. And then you will see, I think that. Yeah, in the second part. Good question. We will come to that in a few slides. Good question. Is the heap bigger than our stack? Actually, it is, but we will never run out of it. We will try to, but it's very, very large. So you will not face the problem in the assignments here.
So yeah, the coded rewrite, it's very unlikely that we will run out of
But
memory.
actually, I think next time we will try to use all the memory on the heap. And let's see how much it is. Yeah. Okay, so in interest of time, I think we should continue. What I want to mention at malloc is the memory we are getting on the heap is not initialized, so we don't know what's in there. We need a new library for that, the stdlib library, and very, very important, if malloc cannot find any space on the heap anymore because it's like everything is already allocated from previous mallocs, then it returns null. So null means you have no more memory available. Very unlikely, but it can happen in some cases, and you always have to check if malloc returns null. Shortly about the casting. So as I said, malloc returns a void pointer. You can explicitly cast it to an integer pointer, of course, if you know it should be an integer pointer. But if you do not explicitly cast it, it will implicitly cast it. We will see that I think on the next slide also. Yeah. So as I said before, malloc returns null if an error occurs. So the error is always there is no more memory available. So let's say again, we have our create array function here. We call malloc and we want 5 bytes and we want to store it in a character R again. So we have in our create array a pointer to the heap somewhere. But let's suppose this malloc fails now because it cannot find any free memory. What happens then is malloc returns null, so it's a pointer which holds the value null. And what you always should do now is after you call malloc, you have to check if the return value of malloc is null, and then you have to react on that. So check if this one is null.
Because yeah, if we wouldn't check for this null pointer and we would want to dereference the return pointer, we would dereference the null pointer, so we would dereference the address null, and our program would just crash if we would try that. So that's why we always have to check if the returned pointer by malloc is null and do something in this case.
So in this case, we have to check if array is null. And if that's the case, we are in a very specific state. We are in a state where there is no more memory available. And in this case, there is only one way to go. We have to close our program and end our program as soon as possible. So in this case, if array is null, return null. So that's like an error code we are handing over back to the main function. And in the main function, we are checking again, if this create array here returns null, then there is no more memory available. And if there is no memory available, we have to end our program immediately. If not, then this if here does not fire, and we go to whatever we want to do back here. So very important, always check for null. There is a dedicated section on our website where we describe you have to do this, otherwise you would get point deduction. And you will also hear that next week a lot in the practicals. So please remember, always check for null when you allocate something on the heap. Another thing is what you asked before. Until now, we always wrote here just 5. So give me 5 bytes. Yeah. Sometimes I want it a bit more specific. Let's say I have here pretty similar array function with create array. I hand over 5. This is in my size character as my size variable here. But what I actually want to do is I don't want to have like 5 bytes. What I want to have is 5 times the size of characters, because I want to store characters inside. Okay, now you can say a character is 1 byte. There is no difference. Yeah, I know. But there are other data types where it will make a difference. So by convention, you usually write here a variable, how many times you want to have your variable. Let's say I want a character array with 5 elements inside. So let's say a string with 4 characters and a null byte times the size of character. So, and if you are here again, check for null and so on. And the second thing we're using here is after this works, we can now iterate, for example, over the array, and we can use this memory. So when we are here and write an A everywhere inside, the actual values here are also set to this A variable, so we can actually use this as an array or as a string, for example.
But yeah, we cannot only do that for character pointers, we can also do that for any type of data type. And for example, we can do that with the data type int. So of course, we can also create or allocate memory on the heap for specific number of integer values. And there are just 2 things that have changed in contrast to the previous example. So we just write here the size of the integer data type, because then we know, okay, we have to allocate 4 bytes times how many elements we want to allocate in the heap. And here we don't have the character pointer anymore, but in this case we have the integer pointer. And again, we don't have to use any explicit cast. We can just use another pointer type. And yeah, we can do again some things in the main function. We can iterate through the array, and of course we always have to check if the return pointer by malloc is null, because then we just want to end the program.
Okay, I have one more quiz for you, because I know that's now it can be a bit confusing in the beginning. Let's see if you really understood what we have talked in the last 30 minutes. Again, I've stated a few statements about this code here. Take your time and mark the ones which are correct. course, you can also discuss it with your neighbors. There are, again, a few very, very tricky things inside. Okay, last few seconds. Let's see. Okay, the easiest one, the value of array at position 1 is 20. That's correct. So we create here our array and we say array plus 1, so not the array at position 1. It's the same when we write it like this. We set this to 20. This one is correct. We can store 6 integers in this array is correct. It's not a typo from myself. Even we create here, create array with 3, and we have here size is 3. There is one big issue inside, and it's size of int pointer. It's not size of int, which should be 4. Size of int pointer is 8. So we are not allocating 3 times 4 bytes, we are allocating 3 times 8 bytes. 3 times 8 bytes are 24 bytes. So we can actually store 6 integers inside because we have allocated 24 bytes. Luckily, and I think it's a mistake here to write this integer asterisk. I would not write it like this. I would say size of int, and then it's more straightforward. But in this case, that's correct. As I said before, we're not allocating 12 bytes, we are allocating 24 bytes because the size of integer pointer. The program does not handle the case if no memory is available. Also very tricky. There is no null check, but we immediately return here the array, so this R. So if there is null, null is returned, and we have the null check here, because array here is then null, so in this case, we are handling null correctly. But I would not recommend it to write it like this. And we override the address of the array in the heap. That's wrong. We have never overwritten that. And with outcast, this will result in a compiler error. Also incorrect. It works like this. So if you compile it, it will work.
Just an implicit cast, so
yeah,
totally fine.
Okay. In the example, yeah, there's one question. Yeah. Yeah, so this mismatch here. So we have an integer pointer and we return a void pointer. So it's also not very, very well made, to be honest, yeah. But what the compiler here does is we have an integer pointer. It converts to a void pointer, which works because void can be everything. So the create array returns a void pointer, and here it converts again to an integer pointer. So both directions work. I would not write it like this. I would also write here an integer pointer to make it more clear, but I want to have as many pitfalls and errors inside as possible in this short code snippet. But yeah, very, very well spotted.
There's another question.
One more, yeah.
Sorry,
Why does it allocate 24 bytes? Yeah. So we hand over here free. So size is free. And we multiply free with the size of an integer pointer. An integer pointer, as every other pointer, is always 8 bytes. So 3 times 8 is 24. Okay, I think we have to continue because we have a few slides left. There is an alternative way to use malloc if you want to have your memory initialized, because malloc does not initialize your values or your memory you have allocated, and this is called calloc. Calloc does exactly the same as malloc, but it also sets the memory you have allocated to 0. That's it. Another thing calloc does a bit different is the parameters. As we have seen before, here with malloc, you always write size times size of int, for example. In this case, this multiplication is done inside of calloc, and you have two parameters, the number and the size of an object, but it is pretty much the same. It also returns null if the error occurs, so that's actually the same thing. And you can use it like this, so call calloc instead of malloc. Everything is pretty much the same as I said before. Don't write size times size of integer, just hand over the size as a first parameter, the size of an integer as a second parameter, and then your memory here will automatically initialize with 0. Sometimes you want that because you want to start with 0. Sometimes if you decide you will anyway write something directly inside, you don't need this overhead of setting it all to 0, then it's okay to use malloc then. We started in the beginning with saying that we have to manage our memory, and our topic is memory management. What does this actually mean? So as I said before, when we do it like this, the heap memory is available until we free it. So it's not bound to the lifetime of a function. It's bound to us programmers. We have to decide when we don't need this anymore. So when we have when we reach this return statement here, we will have memory leaks. There is a program which tells us that we have not removed or freed all the memory we have allocated, and that's called valgrind. We will talk about that next week and maybe also in the practicals next time. But what it actually says is, when your program exited, you have 20 bytes allocated, but they are still allocated, you have not freed it, so they are definitely lost when the program ends. And this is not what we want. We want to remove our garbage after we used it. So you have to do the cleaning before your program ends. And that's with free, you can use that. So free, another function in the stdlib library, and this free deallocates or releases the previously allocated memory. So it's pretty straightforward, I would say. Again, we have the same create array, but what you do after you used your array, just write free array here. And what this does, it kind of removes all of the values here, and it cleans it somehow. So then when you call this valgrind program, it says that you have freed all the memory blocks on the heap. So you have one allocation, one free, no leaks are possible. This is what we want, and this is also what you should do at the assignments, because we don't want to have memory leaks in our programs. Yes? Very, very good question. How does free know the length of the array when we just have the pointer? I don't want to scare you too much, but you have to implement malloc on your own in the third semester. And system level programming, there you will get an idea how this works. In short, when you call malloc, it stores the length of it. And when you call it with the same pointer again, it knows which pointer belongs to which size. So it has kind of a memory inside, yeah. Not the sufficient answer for many advanced programmers, but from now, let's keep it like this. Malloc knows the size internally. Okay, one more thing. Can we still access this area here after we freed it? So we have a pointer to, so we called free here. And when we printed the pointer, it was something like this. Then we freed it and we print the pointer again. And it's still a pointer to a valid address. So free does not change the value of the pointer. It just removes the value or
just the allocated area.
The allocated area on the heap, yeah. So what you could do is you could still access this array on the heap, which you shouldn't do because, again, with Valgrind you will get errors. And this is called a dangling pointer, so a pointer that does not point anymore to a valid object, but you still can theoretically use this. So as a summary, I know we were very fast in the last few slides, but we will give next week a recap about that. And the next week is completely dedicated again about memory management. So don't worry if it was too fast today. But as a recap in your assignments, always allocate as much memory as you need. If you need just 5 bytes, don't allocate 1,000 bytes. That's too much. Always check for no more memory. So if malloc returns or calloc returns null, free the memory after you've used it. So as soon as you don't need it anymore, or latest when your program ends, we will not want to have memory leaks using Valgrind. Then use this Valgrind tool to check for memory leaks. They will give you a good introduction in the practicals to use Valgrind, and we also have one in the test report. So every time you execute the tests on the test system, there is for each test a Valgrind check in the test report. And I think also we have a guide on our website.
So yeah, dedicated sections, just how you should use memory, dynamic memory, memory management, what you should avoid, but also in our style guide and the assessment of assignments, you will find more information on how to use malloc, calloc, any functions related to memory management.
Yeah, and look at our memory management section, as you said. Everything is stated there. And as a short summary, if you have one takeaway for today, the stack, the availability is until the end of the function. The heap, the availability, so the data is available until you free it. When do I use it? You use the stack if you know the size of your array, for example, during compile time. So when you know you program it, you know how big should my array be. And you use the heap for dynamic sizes. That's why it's called dynamic memory. For example, it depends on the user input, so you don't know what the user wants to input. Is it 5 characters? Is it 5,000 characters? Then you need the heap, because on runtime you can allocate memory and get even more memory in memory depending on, for example, the user input. Okay, sorry for the 4 minutes over time, but that was it for today. Thanks for being here and see you next week.
Bye.